Now the talk of Elisabetta CAVAZZUTI from the Italian Space Agency on the GeV LAT observation from GRB and Active Galactic Nuclei.
Sorry, I thought I was on.
No, please, it's not. There is another one. Sit, and stay with me. So I am not alone.
Okay. So thank you to the organizer for inviting me here. I will be as fast as possible, now that I'm between you and the lunch. I'll talk to you briefly about the GeV detection of AGN, Active Galactic Nuclei, and gamma-ray burst with the LAT area, the Large Area Telescope on board the Fermi satellite. Fermi, very briefly, is a NASA mission led by NASA with a huge contribution from Italy, France, Sweden, Japan, and it is basically a converting and tracking system in space, and you have here a tracker and a calorimeter down. It converts gamma rays to a per positron and electron, reconstruct the gamma ray detection, the gamma ray direction from the tracks on the pair. And the calorimeter measures the photon energy and the anti-coincidence. I think I use this otherwise.
That's up to you.
No, because perché non c'ho il per mandare avanti questo. Okay, so it has a wide field of view. It looks at the sky, 20% of the sky each time, and it is in a survey mode. So, Active Galactic, this is the sky before Fermi. We were used to have ICRANet, which operates up to 2000, and we had about more than 200 sources. Now we have over than 5,000 sources out of 8 years of data integration. And these are the two maps of the sky with ICRANet on the top left and Fermi on the bottom right. So Active Galactic Nuclei, very briefly, you have seen already this picture. It's about a bruised picture, but shows you a kind of unified scheme published in 1995 by Ari Padovani, where you can understand which type of AGN you are looking, depending on the line of sight of the observer. And I will concentrate on blazars, which are those active galactic nuclei you observe when the line of sight is in the direction of the jet, so when the jet is pointing towards you. There is a simple emission model, seeing two bumps in the spectral energy distribution. The left bump is the synchrotron, and the right one is the inverse Compton. You can have a leptonic and hadronic model explaining the second peak, inverse Compton. The first one is made by electrons and magnetic field by Bremsstrahlung. They emit synchrotron photons, which are upscattered to higher energies and are upscattered to higher energies depending on different models. You have a leptonic models where you have the synchrotron self-Compton, which means that the same electrons of the synchrotron peak are upscattered to high energy, or they interact with external photons and they make an external Compton. Or you have an hadronic model where the high energy emission is dominated by proton synchrotron, pi-zero decay, and synchrotron and Compton emission comes from secondary products of pions. So leptonic models can provide good fits to many blazars. This is a result based on LAT data by Bolokovic in 2016 on a high-peaked BLAC, Markarian 421, where you can see that the peak, the Compton peak, and the LAT data are able to be fitted by a leptonic model. This is the same object in the same paper with different energies and light curves. On the X-ray, you have the time, and on the Y-axis, you have the energies at different wavelengths, radio from the bottom, and UV, and then X-rays, and LAT, and then TV. The top one is Veritas and Magic. And then you have that these models can provide good fits of these blazars, and you have that X-rays and gamma rays emission are often correlated. While the hadronic model for which the cooling times are longer, they have more difficulty in explaining this the rapid variability we see in these blazars. So this is the 3C279, a light curve in a paper on 2016, where you can see the light curve above 100 MeV, and the green and the red dots are in 5 and 3 minutes time beams. This source was able to be fitted with the LAT with such a short time beam. This is the SED, where you can see on the top, on the inverse Compton bump, the huge difference in flux here, how it experienced the flare in different years. So these are different observations, not simultaneously, but then you can have the red and the blue here, and again, to see the variability. So oops, yes. So in many cases, both leptonic and hadronic can explain this SED. However, you can have some diagnostic to disentangle between leptonic and hadronic, variability, X and gamma ray polarization, and neutrino. For variability, because, okay, leptonic you have correlated synchrogamma variability, while in hadronic you can produce uncorrelated variability and orphan flares. So the X-ray gamma ray polarization, this is a work on 2010 by the LAT collaboration, when the same blazar, 3C279, which is a flat spectrum radio quasar, undergone a huge flare. But what is interesting here is this panel, optical polarization degree and angle. We have a swing. You can see that in coincidence with the flare, in coincidence with the flare top panel, where you have the LAT data, you have a change in polarization angle. This means that optical and gamma rays emitting region are co-spatially. And I don't talk about neutrino because you have already heard a lot about it, and you will hear more about next week. So what about the unified scheme? I presented at the beginning, 1995, we had a scheme based on the classification of the objects on their optical spectrum, flat spectrum or BLAC, depending if they have broad emitting line or featureless optical spectrum. But this may be superseded by a better knowledge thanks to the many observatories we have, Fermi, X-rays, and deep radio surveys. So this is a new classification scheme suggested by Padovani, and it is mainly based on physical difference than just observational difference. So the presence or the lack of strong relativistic jet, and we can classify the object if it are jetted or non-jetted, where by non-jetted I mean that the jet are weak. So we have that the SED of non-jetted AGN have a cutoff at much lower energies, so we can't detect them at a higher energy, and these are those objects which are more misaligned, let's say, with respect to the line observer line, and then respect to the jetted AGN. In fact, these are two types of objects very well known: Centaurus 6, which is a radio loud object very nearby, it's a radio galaxy here behind the door, or Markarian 473, which is a radio quiet, means that the ratio between the radio and the optical emission is below a certain value, which is 10. So the jetted AGN are characterized by strong and relativistic jet, while the non-jetted AGN may have radio structures similar to outflows, but these jets are small, weak, and slow with respect to the jetted one. All AGN are powered by a supermassive black hole. We can so radio quiet and radio loud, and we have non-thermal emission over the whole electromagnetic spectrum for the radio loud AGN, while the radio quiet are more dominated by the thermal emission. The most striking difference is in the X-ray and gamma ray band. This is why I'm talking about this, because Fermi has made difference. And so to distinguish between these two, we should have detection in the MEV region, for which Fermi is not well suited because it's better suited at GeV emission, but as well up to now is what the best we have. This, now we can move, I like to move to the study we can make with data and population studies with all this information from Fermi. These are Fermi catalogs. This is the sky after 8 years of integration, above 100 MeV, more than 5,000 sources, and there is a work by Sbarrato and collaborators in 2014 based on the catalog of Fermi, the second LAT AGN catalog, where they try a connection between accretion rate and relativistic jet power in AGN. The jet power can be traced by gamma ray luminosity, and the accretion disk is traced by the broad emission line. So they took this catalog, they made following the classification published in the catalog, they made this plot with the luminosity of the broadline region with the Eddington luminosity. You can see that there is a difference between the red dot, which are the flat spectrum radio quasars, and the blue dot, which are the BLAC, which are those objects in which the jets and the optical characteristic may make a difference, and the position of the existence or not of the broadline region. So there is a tight relation between this accretion rate and the jet power in Blazar, as you can see. If we add radio galaxies, which are those objects where the radiation mechanism is less efficient, we can see that the slope of this relation is steeper if we move. Here are the low emitting gamma rays, the low energy, radio galaxies, which are the progenitors of BLACs, but if this radio galaxy would be located, if they were beamed according to a Lorentz factor of 3 or 10, they would move to the right, and so we can study the radiatively and efficient accretion regime only through the radio galaxies. Fermi has also detected the most distant blazars up to now. The most distant is an MVSS at a redshift of 4.3, and if this is the distribution of all the objects in the third catalog of AGN, these highly redshift blazars are here, up to the right end of this plot. This means that this is the object with a redshift, with a magnetic black hole mass between 8 and 9 solar masses, and the detection of these distant blazar and powerful could be important to constrain the space density of massive black holes in the early times. At higher energies, Fermi has also published 2 catalogs above 10 and 50 GeV, and I like to go back and forth between these pictures. You can see here the detection is above 50 GeVs, fewer photons. Here is only above 10 GeV. You can see how change the sky. And on this data, Fermi has published this catalog where you can see that the objects we can detect displays, this is a plot which shows you the distribution of the peak of the synchrotron energy distribution of the blazars, and the green is the distribution of the objects detected above 100 MeV, the red is above 50 GeV, and then we have the violet, which is a middle way. And you can see at above 10 GeV, you have a sky much more similar than above 100 MeV. So above 50 GeV, we have another sky. This is important. And this is a plot which shows you the distribution of the synchrotron peak position with respect to the photon index, where we can see that there is a strong correlation and a hardening of the high energy spectra with the increasing of the peak frequency of the synchrotron peak. And this correlation and hardening is even more pronounced above 10 GeV. This is due to the EBL attenuation suffered by higher energy, higher redshift sources. And finally, before to move to the GRBs, we have a plot which shows you how Fermi is able to put all, to well resolve the high energy peak of these blazars. On the top panels, you have the data from the 3FHL combined with the one, the 3FGL, so from 100 MeV up to hundreds and GeV. And this is really important for the connection between GeV regime and TeV regime, the Cherenkov telescope on ground. We can see that sources become softer at higher energies and a higher redshift. So moving to the gamma ray burst, you have already saw this picture. We have a prompt emission and an afterglow, which are based on non-thermal emission, the jet energy dissipation in the prompt phase, and jet interaction with the ambient medium in the afterglow phase. The prompt emission scales about milliseconds to minute, while the afterglow is on days and months. How are the GRB detected by LAT? We can see, compared to the low energy emission, because Fermi has two detectors, the gamma ray burst monitor, which is at lower energies, and the LAT, the large area telescope above 200 MeV. And we can see that the bottom panel shows you the emission detected by the large area telescope, where we can see a delay in the onset of the emission with respect to the low energy. And it even not only delayed in time, but it also persists longer with respect to lower energy and can be fit by a single band function over 6 decades of energy. This is a result based on even LAT data, where you can see this correlation, which is confirmed by the first catalog of GRB published by LAT, and we are working on the second. Between short and long GRB, we have that we can, with LAT data, calculate the mass and the spin of the black hole. The top table is on long GRBs, while the bottom table is on short GRB, and you can see here the masses of the black holes, which are similar, and this is the accretion, the critical mass of the black hole. And this is the GRB catalog, where again you have the top black and red dots are long GRBs, while the blue dots are the short GRBs, which are in agreement with the plots I showed you before. And I think I can conclude here, leaving you the fact that Fermi has won 4 Bruni Rossi prizes, and we hope for a first.
Thank you so much. Just a few questions.
I have a very basic question. What is the difference between this jetted and unjetted classification versus FR1 and FR2?
So now so is not between FR1 and FR2, is more based on understanding the difference between the AGN, not anymore based on observational characteristic as were the optical spectrum. Up to now we were distinguished between flat spectrum radio quasars and BLAC based on their optical spectrum lines. There are some objects, BLAC and flat spectrum, which change classification during the time. We have cases, and this is shown in this plot. We have cases here where there are this BLAC, and you can see here BLAC flat spectrum or flat spectrum. So this object changes during their time. So we understood that the classification on optical spectrum was not anymore reliable, and we tried to move more to physical difference. And these are both jetted AGNs, but possibly the difference is that some are more jetted, more powerful, with a different black hole, let's say accretion rate, and others more inefficient accretion rate. The fact that BLACs and Farahnov-Rayleigh 1 are possibly connected, because we think that if you take a Farahnov-Rayleigh 1 and you point the jet towards you, you see a BLAC. This is still the underlying model. We are trying just to connect these two classifications to the real physical parameters of these two objects, seen at different viewing angles.
Wait a minute.
One very specific question. Can you be a little bit more specific about the relationship between accretion rates and the jet power in blazars? Can you be a little bit more specific?
If you in these plots, you mean? What do you mean about more specific? Sorry, I may quantitative or.
What can you observe that gives a hypothesis in terms of the the essential natures of blazars via the accretion rate? Can the accretion rate itself help you to determine what you might call or falsify certain parts of your models or your model building on blazars?
So in these works, Barato is trying to connect the emission with the jet and the disk and trying to understand if moving to objects which have an inefficient accretion regime, the disk and jet and disk connection is less obvious. But it's what I only can tell you. Sorry. It's a work, yeah, yes. It's yes. It's no.
How long will it take?
I hope they will work on more data. The point is that in this plot, what is astonishingly missing is the number of BLX, because to evaluate a luminosity, you need a redshift. And for the vast majority of BLX, we do not have a redshift because of their featureless optical spectrum. So this is the point. We have observed a lot of BLX, even with the CAC, for hours, and we couldn't detect any emission line, even weak, or a calcium break. And so I don't know how can we inject BLX in this, and we are missing this big part of the picture. So I don't have a solid and reliable answer to time, how long it will take.
Thank you.
You're welcome.
Okay, thank you so much, Elisabetta.